And by doing that, you have basically infinite, the chances that you can scale are infinite, because in the existing pool of resources, you can just extend and add, parallelize the processes. The horizontal scaling is more complex to implement, but it's more cost effective. So with vertical scaling, at one point you can scale up and go doubling the CPU, the memory, but you will hit the ceiling. You cannot go above the largest instance possible. So vertical scaling means that you extend the existing instance, for example, from 8 CPUs and 16 gigabytes memory, you go to 16 CPUs and 32. Then you realize that you need to extend and you go to the next, but this has limits. With horizontal scaling, and I don't want to skip this, as some applications are read mostly applications, like 95 or plus% reads, even though this is not scaling in the way that you scale reads and writes. It's still with MongoDB possible that you can spin up to 50 members in a single replica set and deploy across different data centers and regions across the world, make the database close to your applications, and you can scale your reads. So this is just for read scaling. But the real scaling, the horizontal scaling, is when you split your database across multiple shards. And so you don't hit a single primary with your application, but instead you will have the data partitioned across multiple shards. And like in this example, we have a total 1 terabyte of database. If we split that database across multiple shards, then we can run on more cost-effective hardware, and still in this existing pool we can add as many nodes as we want to. So how is this done with MongoDB? If we look at example where we have a standalone app and there are multiple tenants that are deployed and use a single database, this is how most of the applications are built at the beginning. It's just one single database. All the tenants are stored in the same database. It's not very good model to scale. So one of the options that you can do and will allow you scalability is basically if you can deploy database per tenant. So instead of all the tenants will be using the same database, you can have multiple databases per tenant. One additional database that you may need is a catalog database where the metadata will be stored. So when you want to query the data for tenant B, then the metadata will be taken from the catalog, and you know where to route your queries. And that can be extended where, for example, if you have a large tenant, let's say tenant A can be fit into its own replica set, the catalog database will be updated that your application knows where to send the queries, and tenant B and C can run into shared database. So this is a shared multi-tenant replication. And you can extend this up to having every single tenant in its own database. Of course, there will be the catalog database where you store the metadata. And this is fairly good scalability model if you know approximately that all your tenants can fit and run into single replica set. But sometimes even a single tenant, let's say tenant A, will scale and grow, and so that it doesn't just fit into a single replica set, and you will need to shard that particular tenant. So in MongoDB, there is that sharding method, sharded clusters, which consists of shards where a subset of your data is partitioned. As soon as you deploy MongoDB sharded cluster, then adding multiple shards is just a matter of running one command through the Mongo router. And there is the metadata or the catalog database that we talked about, where the router will exactly know where to route the queries and in which shard what database exists. So the sharded cluster is composed of shards, MongoS, and config servers. The shards are basically where your data is saved. Every database has their own primary shard. And that's decided when you create a database on a sharded cluster. The balancer will have the information about all the shards based out on the dbstats command, and the primary shard is assigned to where it's with the lowest data size. So initially, when you shard a database, it has already primary shard assigned. Any additional databases that you create across the shards will have assigned a primary shard that is with the lowest data size. And that is important for the balancing and the data distribution. It's important to mention that if there is a collection that is not sharded, like in this example, the collection number 2, that collection only exists with its full data set on the primary shard for that database. Anytime your application routes read or write requests to that collection, it will only go to shard A. So in this example, it's expected that shard A will have more load compared to shard B, just because there are collections that exist and are not sharded on the primary shard. So this is important for non-sharded collections. The config servers are just where the cluster metadata is saved. Not only that, but on the config servers there is the admin database where the users and roles and the authentication information is saved. After MongoDB version 3.4, the balancer process runs on the config server primary node, and it's usually running on port 27019. And the last, yes?
One question back on the previous slide, the previous one. Yeah. So on the collection 2, you said not sharded, and that's why all the queries or requests MongoOS router directs to the sharding. But at the same time, since the collection 1 is sharded.
Yes.
So does it mean like, so Mongo router, the MongoOS now knows that like all the load is happening on the shard A. So I can redirect the collection 1, the load to the collection 2. That way I can balance between shard A and shard B.
Yes, so the collection 1 is sharded. It will be split into chunks.
Right.
And every shard will have equal number of chunks. That is how the balancer distributes the number of chunks. It still doesn't mean that every shard will have equal data size, but the collection, as it's split into chunks, the balancer will just move half of the chunks on shard A, half on B. When a query is routed, it will depend where is that data for that document in what chunk. If it's on A, it will direct the request there. If it's on B, it will direct the request on B. For collection 1, that is how MongoS, it has the metadata where to route the queries. For collection 2, the metadata tells that it's always on shard A, so it will always go there. It doesn't balance the load based out of whether shard A is overloaded, so let me send the request to shard B. It only balances, it sends the request where the data is. So if most of the data is on shard A, that's where the request will go.
There is no dynamic rebalancing that happens to redistribute the data based on the workload that is happening?
No, it doesn't balance based on the workload. So yes, MongoS will be caching the metadata from the config servers. The config servers have the metadata for the entire cluster. The data is split into chunks. Each chunk has boundary from the min key up to the max key. And so when you are sending a query, the MongoS will know exactly where that document is into which chunk. If you are doing a range query, then if MongoS has to send that request to every single shard because it doesn't include anything from the shard key, it doesn't know where that data might be, then it will send broadcast operation to all of the shards. The shards will return the request to MongoS, and then MongoS will merge the result and send it back to the driver and the application. Okay. So when you want to shard and choose a shard key for a collection, there are some principles that you will need to look for when making a decision on the shard key. The first one is the cardinality of the shard key. You will want to have a shard key that has relatively high cardinality, and that is how many unique values your shard key will have. If we have just 10 different unique values for a shard key, then we cannot make splits. So your data will be only partitioned into 10 different chunks, and that's the maximum that you will get. So it's good that you make a decision on a shard key that has very high cardinality. But even if your shard key has very high cardinality, you still need to look for the frequency, because some shard keys might be with very high frequency, for example, between 1 and 1,000 different values. If you have a shard key that 100 is mostly going to be in the inserts, then that shard key will cause a problem of its frequency. It will keep growing, and again, you cannot split when a shard key has very high frequency. And the third one is monotonically changing shard keys that will grow over time, like a timestamp, or maybe auto increment key that just keeps growing over time. Those shard keys are also bad if you are using range-based sharding, because at one point all of your inserts will be going up to the max chunk key, and that will cause all of the load to go on the shard where that chunk will exist. So when you're choosing a shard key, it's best that you will choose some key that is included in most of your queries, if not at all. So you will need to understand how you will query that data. What is the key that you will be sending from the application? You don't want a huge number of documents to be sharing the same shard key. That is really what it comes to, the shard key frequency. And if you are doing range-based sharding, you will want to basically make sure that your data that will be close to each other will exist in the same chunk. So when you query, you hit a single shard instead of doing a broadcast operation. So a chunk is basically a continuous range of shard key values. The lower boundary is inclusive, the upper boundary is exclusive. So if you have a range between 1 and 10, 1 will be inclusive, 10 will be exclusive. The default size is 64 megabytes. It's configurable between 1 megabyte and 1 gigabyte. And the balancer will just migrate chunks from one shard to another depending on some migration thresholds, which are shown in this table. And that's basically the only thing that the balancer does in MongoDB. It gets how many chunks exist on one shard. It gets the number of chunks on the other shard. If there is a migration threshold met, it will just move chunks from one to the other. Or if there are multiple shards, then it will make a decision what is the shard with the lowest number of chunks, and then try to rebalance the number of chunks. With this process, the balancer doesn't balance the data at all. The assumption is that the chunks will be with the same size, and so then you will get equally distributed data. Just by equally distributing number of chunks, you don't get equally distributed data. Yeah.
So is the data is not redistributed, only the chunks is get migrated?
Yes, with the chunk migration, you will only move documents that exist in that chunk.
So that data migration?
Yes, but some chunks might have 64 megabytes, or depending what is your chunk size, some chunks might be empty. For example, if you expire data, if you have, and I will get to that soon, if you delete documents, that chunk is empty. It's still counted as a metadata. The balancer may move that chunk to another shard, and it will think my data is rebalanced. In reality, what happens? You're moving just a metadata with 0 documents. So you will have equal number of chunks, but your data will not be evenly distributed.
So is there a threshold for, like the chunk size 64 MB, is there a threshold for that 64 MB of chunk translated to how much of data set?
There isn't. There is no information in the chunks metadata how much data it exists in that chunk. The assumption is it's the setting that is for the chunk size generally on the cluster, which by default is 64 megabytes. Okay. There are two types of sharding. One is range-based. The other one is hash-based. So with range-based sharding, you are splitting the data into ranges. And those ranges are basically determined by the shard key values. For range-based sharding, it's good that you have high cardinality, low frequency, and your shard key is not monotonically increasing. With range-based sharding, if you have range-based queries, then it's more likely that with your queries you will hit a single shard because your data will be close together. With hash-based sharding, MongoS will use a hash function, and based out of the hash function, there will be a hash key, and the balancer will decide in what shard it should move that document. Now, with this type of sharding, documents with close IDs might end up in different shards and chunks because the hash key might produce value that is not close one to another. So for hash-based sharding, monotonically increasing keys might be good because it has very good cardinality, and mostly those values are unique. So you will get very equal data distribution by using these keys. And the application doesn't need to compute the hash. This is only done on the MongoS layer.
So do I have an option to define my own hash if I need to, just in case I feel my hash function is more efficient than what MongoS computes?
If you want to make your hash, you can do that, but you will still, if you enable hash-based sharding in MongoDB, MongoDB will compute hash on the insert that you do on that key. So you are inserting some key, and MongoDB decides to make an index that is hashed, and it will always hash it. If you want to do a hash on your application, then you can probably do range-based sharding and split your hashes into ranges. So you'll have to know what you're doing with the hashes. And the last piece is the balancer, which is a process that it basically monitors the number of chunks per shard, and then it decides to move chunks across the shards. So if we have a cluster with 3 shards and shard 1 and 2 have 6 chunks both, ideally, if every chunk is 64 megabytes, then what happens when you add shard 3 in this cluster, the balancer will say, I have my migration threshold of 2 chunks. I will need to move chunks from 1 and 2 to 3, and it starts the migration. At the end, what the balancer will see, 4 chunks per shard, everything is equally distributed. If the chunks are 64 megabytes each, you have equal data distribution as well. So this is ideal, but in reality, that might not be the case. So let's take a look at the real example where we have a collection tracking, and in this collection tracking, we are saving documents for assets that are being tracked real-time by GPS. Every document that we're inserting has information. What is the client ID? What is the asset ID that belongs to that client? And at what time that GPS location was pushed into the database. So there are tens of thousands of clients that are inserting data. Ranges between tens of hundreds to thousands of assets per client, and there are millions of documents that are inserted on the cluster every minute. One extra requirement is that after 1 year, the data expires. So you only need to keep this data in your cluster for 1 year. After 1 year, there is a TTL index that automatically deletes the documents based on to the pushed add key. So eventually, the data that you're inserting after 1 year, it gets expired. And at the same time, there is a requirement that the queries that will be sent to this cluster is a client will send a request to get the trajectories for their assets in a time range. So the query will look like, for this client ID and this asset, give me the time ranges between pushed at. And so if we look at the shard key options here, there is an option to just shard by the client ID. And every client that sends the request will only live on a particular shard or shards. And as an option, this shard key will have very relatively high cardinality, but very high frequency, because every client will have hundreds to thousands of assets, and every asset will generate hundreds to thousands of documents every single day, which makes not efficient shard key to have. Additional option is if by the client ID we have the asset ID, and in this case again this shard key will have very high frequency, because for the same client ID and the same asset ID on a daily and monthly basis, there will be documents that will have very high frequency. So the next option is, if we do exactly with what is the request for the reporting, for each client and asset ID we partition with the pushed at, which is the date. And so this shard key has very high cardinality, relatively low frequency, even though some of the assets might be pushing a lot of data if they are more active compared to others. So some assets might be just active, some other might not be. But this shard key is more ideal if we look just partitioning by client ID and asset, or just by client ID. But even if we initially make a decision to shard on client ID, after MongoDB version 4.4 there is an improvement that you can refine the shard key, and you can do that by running the command refine collection shard key, add the new shard key, and MongoDB will change the shard key. Even starting with version 5, there is another improvement where you can reshard your entire collection by making decision on completely new shard key. So in this example, you can go with a shard key that is a combination of your asset ID, and you can go with hashed index on the pushed at date time. But even with these improvements that were made in MongoDB since version 4.4, there are still some things that could be improved based out of what we have seen. One of the things that could be improved is the balancing process. As we already mentioned, the balancer is just making sure that every shard in the cluster has exactly the same number of chunks. The balancer has assumption that every chunk is with the same size. But that is not always the case. Like in this example, we have a TTL index that is expiring the data, and those chunks that are the oldest chunks eventually get their data expired, and every chunk exists as a metadata in the cluster with 0 documents. So if you look here, some of the chunks have expired data, are being empty, some chunks are expiring, so there might be half empty, and other chunks might be very close to 0. So the balancer here has done its job. Every shard has 4 chunks, and it's equal. What is real is your data is balanced like this. Shard 2 has most of the data, shard 1 and 3 a portion of the data. So what you may see is in your monitoring, and maybe you will get alerts that Shard 2 has very high CPU utilization, your working set is large, and you may be wondering what's going on because the balancer is showing equal number of chunks. Well, in reality, it has equal number of chunks, but it doesn't have the metadata. So the balancer thinks, yes, I have distributed my data, my chunks are equal, and this is what you get. So really important to know how much data exists per chunk. And one of the things that might be improved is if the balancer has the information about the data size for that chunk. If you look at the config database chunks collection, there is no information how much data exists in that chunk. It's just information what is the min key, what is the max key, and that's basically everything. So if you want to check how much data actually exists in that chunk, there is a command in MongoDB, data size, that you can run based out of the range from the min key to the max key, and that will give you exactly how much data exists in that chunk. Using that data, then you can make a decision. Is that chunk empty or it has data? If the chunk is empty, really, ideally what you would like to do is to merge that chunk with its neighbor. As that is just a metadata in the cluster, you can merge two chunks that are neighbor chunks. The problem in MongoDB in the sharded cluster is that you can only merge chunks that are neighbors and exist in the same shard. If the neighbor chunk is on another shard, you can still merge, but you will need to bring both chunks to the same shard, and that's where you can merge. By doing that, what you will do to rebalance the data is basically, if on shard 1 the neighbor chunks are merged, then we are reducing the number of chunks. Now the balancer will see that, and it will say, I have greater number of chunks on shard 2 and shard 3. Shard 1 has lower number of chunks. I need to migrate. The problem is when the balancer starts the migration, internally in the algorithm, what it has is it will make a decision to move a chunk that is not being used. If shard 2 has all of the chunks that are being used by inserts, updates, those chunks are considered to be busy. The balancer will find chunk that is not being used at the moment, and it will migrate that chunk over to the shards that are missing chunks. So what might happen in this example is that instead of the 48 megabytes chunk moved there and have some data distribution, instead what you might have is another empty chunk from elsewhere. It's being moved, and you don't really have a data distribution, but you will end up again with just equal number of chunks across the cluster, and that's all. So this process needs to repeat again, merge the empty chunks with the neighbor on the same shard until you merge everything. And as data expires, if this is the case with your application, you will just keep generating empty chunks. The balancer doesn't have any idea whether a chunk is empty because there is nothing in the metadata, and there is nothing like internal thread inside the database that will take care of this for you. So one improvement that might come out of the next MongoDB versions is exactly this. Empty chunks are being generated. Internal thread will take care of that. Maybe the chunks will have a metadata associated, so the balancer, instead of just migrating chunks, it will be migrating data with the chunk migration. And on this slide, we have the steps that are being taken when the balancer is moving chunk between shards. So there is a source shard, there is a target shard. I don't want to go into the details. I just want to point out that when a chunk is being migrated from source to target, on the target, it needs to update the metadata to the config server. So instead of my chunk is on shard A, now my chunk is on shard B. When that metadata update happens, it makes a collection level lock. So even if it's for a few seconds, it doesn't only lock the documents that exist or should exist in that range, and with wire target engine that should be possible, but it does collection level lock. So one important thing, and if you are doing chunk migration on a busy times for your application, there might be increase in your reader and writer queue, and you will see something like this in your monitoring, where you may see drop in the wire tiger tickets, whether it's read or write tickets, and you probably want to enable the balancer into its own balancing window and just run rebalancing in the off-peak hours. Another important thing to mention about the rebalancing and the load on the clusters is that even though MongoDB has their monitoring tools like Ops Manager and Cloud Manager, there is, of course, PMM, Datadog, other monitoring tools. Sometimes it's just not easy to see what's going on the cluster level. You might be easy to see, it might be easy to see what's going on a shard level, on a particular primary for that shard, like what are the total number of inserts, operations, document scans, what is the CPU utilization, memory utilization. But there is nothing like a global view that you can see, okay, so this is my MongoS, these are the shards underneath, how much load is going through every shard, some visibility that you can easily see what's going on. You can drill down at the very bottom what's going on, but there is not, at least I have not seen something that will show you from top to bottom how is the load distributed. And you mean moving chunks between?
Yeah, so let's say I'm moving chunks and then there's a power cut or something and I'm in the middle of moving a chunk. So is that taken care of?
Yes, so the balancer has steps if and moving chunks might also fail at some point. So there are threads that in your database, the data directory, you have move chunk subdirectory. That's where the documents initially are being moved. And when there is a successful operation, there is another thread that will delete the documents from the old shard, and the metadata gets updated on the new shard. So with the latest MongoDB versions, there is a mongostat command that, for example, if you are facing with new cluster that doesn't have any monitoring at all, you can still use this. There is the option -O that basically everything that exists in the DB server status output, you can put that metric and monitor what is going on in real time. So this command is saying interactive mode, every 5 seconds refresh data. The downside of this is that you will need to have that command handy and ready, so you copy paste on a MongoS instance, connect to the cluster, and whatever metrics you don't want to see, you will just have to delete, put the command again. For me personally, it might work better if there is something like the top command on Linux, where you type top and then press F key, and then you choose what are the keys that you want to include or exclude from the output. Something like that might work better, but even this is something that you can do on new clusters, where you just want to see how many connections you have, what are the index scans, document scans at that particular time, that will give you some input, what is going on with the cluster. And for summary, the balancer really, with the current MongoDB versions, the balancer really just takes care if there is an equal number of chunks per shard. It doesn't have any information if there is an equal number of data per shard. When there is a migration between shards for a single chunk, at the end there is few seconds metadata lock and its collection level lock. It's not locking just the documents that exist in that chunk, but it's a full collection lock. So that might cause issues if you are running on a busy period with your application. When a chunk is migrated, 3 write operations happen. So the chunk is first written into shard A. Then, when it's migrated, it's copied over to shard B and deleted on shard A. So ideally, you should think of having a shard key and balancing your data without the balancer to have to do much work on rebalancing data across the shards. Ideally, that should be 0. Like if you have chunks and if you know how to pre-split your data, that would be ideal, to not even include the rebalancing. And always try to choose a shard key that will not do broadcast operation on your cluster. That means that it should target a single shard at times. Choose shard key that is included in most of your queries and with high cardinality. When you add additional shard to the cluster, there will be rebalancing of data. Data from other clusters, from other shards, will be copied over to the new shard. That doesn't happen instantly. So you may have to wait days or even weeks, depending on the data size, before that data gets redistributed. And if you have databases with small collections and large collections, you need to make a decision what collections you want to shard. Sharding small collections might not be very efficient, because with small collections, the overload that you will get with searching across different shards might be more expensive, instead of just having the collection unsharded and existing on the primary shard. And if your working set fits in replica set, if your working set doesn't grow, if your data is properly indexed, if you are monitoring your application and you know that vertical scaling will work, better use vertical scaling instead of doing sharding. So avoid sharding if you can manage to run your applications with replica sets, and if you know that your working set fits into single replica. Thank you, and apologize for the beginning that we had some technical issues.